Okay, so this talk is going to be about vCorfu, and vCorfu is what we call a cloud-scale object store on a shared log. Now, this is a huge project that we've been working on both at VMware Research and with engineering and product teams within VMware. And it's the product of a collaboration with collaborators from over 3 different academic institutions. So with that, let's get started. So I'm going to start by presenting some background on shared logs, since vCorfu is a cloud-scale object store built on top of a shared log. In the age of the cloud, we now know that systems which are simultaneously scalable and strongly consistent can be pretty difficult to build. So systems based on shared log, like vCorfu's namesake Corfu, represent a point in the design space where you have consistency without compromising scalability. However, shared log systems make a different set of trade-offs. Even though writing to a shared log provides strong consistency and very high write performance, previous work has shown over 500,000 operations per second, to provide the strongest levels of consistency and concurrency, these systems usually use a technique called state machine replication and log-only updates. So for example, instead of writing the new value of a counter, we would write an increment record onto the log instead. The consequence of this design is that reads are now slightly more expensive, since clients have to read all the updates to figure out what the current value of the counter is. So our experience with the Corfu design with real-world applications have identified 3 points where the scalability of a shared log could be improved. So first, clients may have to read several unnecessary updates in order to service requests. For instance, even though all of this client might be interested in is reading the value of the object B, it might have to read the other objects, in this instance, object A, to determine what the current value of B is. Second, since updates are ordered in the log temporally, updates for any single object may be scattered across the log. And a client might have to contact multiple nodes just to read a single object. Finally, in the context of transactions built on top of these systems, clients may have to do extra work to determine whether an entry is valid or not. In this case, a client encountering this entry that modifies an object B may have to figure out what the current value of object A is in order to determine whether this entry is even valid. So vCorfu is really all about addressing read scalability. And that enables vCorfu to scale to systems that have a large number of consumers on the log. So in this talk, I'm going to introduce 3 of the key mechanisms of vCorfu. The first is a technique called stream materialization, and that localizes related updates and enables client requests to be serviced without each client playing back the log. The second is a technique called composable state machine replication, and that enables vCorfu to support very large state machines that don't fit in any one client's memory. And finally, I'll introduce a mechanism we call lightweight transaction resolution. And that eliminates the need for clients to determine whether transactions in a log were aborted or not by resolving transactions before they're recorded into the actual log. So of course, vCorfu is really just another point in the design space, and itself is not without trade-offs. For example, our stream materialization mechanism introduces a significant penalty at the cost of writes. However, we argue that this is a pretty small trade-off to make, since we can now service a lot more clients as we've greatly reduced the cost of reads. So by the end of this talk, I hope to show that vCorfu enables shared log systems to scale to cloud-scale size data stores, and while offering comparable performance that outperforms state-of-the-art NoSQL systems like Cassandra, all while retaining the strong consistency benefits of a shared log. So in the next section, we're going to dive right into shared log systems, which is what vCorfu is built on top of, and go over what really makes them tick. Then we'll show how vCorfu modifies shared log systems to greatly improve read scalability. So when I say shared log system, I really mean systems like Corfu, which vCorfu is based on. Shared log systems have really two basic operations. The first is append, which simply puts an entry at the end of the log and returns the address that was written at. And read, given address, returns an entry that was previously written to the log. So this API really enables shared log systems to operate at unlimited concurrency without sacrificing consistency, since writers can never overwrite one another. Now, scalable shared logs are built from 3 primary components. The first is a sequencer that keeps track of the tail of the log. You can have log replicas, and they serve as really the persistent storage for the log, and a layout that describes how addresses in a log map to log replicas. So to see how all these components fit together, let's take a look at how we would append to a shared log. So to append a shared log, you usually have a client, and it'll contact the sequencer. The sequencer would issue the next address in the log. Using the layout, the client determines which replicas it should write to. The client then writes to the log using the address that the sequencer issued it, and the write is considered completed once the client is done replicating. Now, by separating control, or the issuance of addresses, from the data path, which is the replicas where the data is actually written, shared log designs enable clients to append to the log at a very high throughput without being bottlenecked by I/O. So in vCorfu, we take the Tango approach to build an object store on top of a shared log system. So clients don't interact with the shared log directly. They interact with objects that are managed by a runtime, which manages interactions with the log. And in vCorfu, we built a runtime in Java, and that automatically takes plain Java objects and turns them into vCorfu objects. You can read more about that in the paper. But objects are stored in virtualized logs we call streams. Each stream contains a set of updates for that object, and the objects are replicated using state machine replication. So, for example, if this diamond object were a counter, 2 operations might be increment and decrement. The actual value of the counter is not recorded, and only the operation on the counter. So again, this really enables concurrency without sacrificing consistency. So the Tango approach also leverages the log to provide rich transactions, which vCorfu also supports. Clients execute optimistically on views that they have in memory, and the runtime uses the log to serve as a ground truth whenever a conflict might arise. So now that I've described the shared log systems that vCorfu is built on top of, I'll now go in and really describe the architecture and design of vCorfu, and I'll specifically focus on the features of vCorfu that really enable it to provide really high read scalability. So in order to achieve really high read scalability, at the heart of vCorfu is a new building block we refer to as a materialized stream. So materialized streams greatly simplify reading streams, since clients can use a materialized stream to find all the updates of a stream without sifting through this global log. Materialized streams are implemented using stream replicas, which store materialized streams. Stream replicas are like log replicas, except instead of being indexed by the global address, they're indexed by a combination of the stream ID and the stream address. So our vCorfu sequencer keeps track of not only the tail of the global log, but the tail of each stream, as well as the stream address, which is simply just the counter of the number of entries in each stream. So to kind of see all this in action, let's take a look at how materializing a stream works. So streams are materialized as clients append to the log. During an append, clients request an address from a sequencer, and now the sequencer, or giving the sequencer the ID of the stream they wish to append to. So in this case, the client wishes to append to the triangle stream. The sequencer issues a global log address and a stream address. We've kind of omitted the global address for clarity. In this case, the append is assigned global address 2 and stream address 1. The client then finds an appropriate log replica using the layout and writes using the global address. And then the client finds a stream replica using the layout again and writes to a stream replica using the stream ID and stream address. So an important component of the stream materialization protocol is that it has a requirement that clients have to commit data to every log and stream replica they've written to. And that's because materialized streams are dense and they don't contain what we call holes. As optimization, the client doesn't need to send a commit message to the last replica it writes to, since the commit message is piggybacked on the write message. So also log replicas and stream replicas only serve data which has actually been committed. So the extra commit message does impact append throughput. So this is a trade-off we were mentioning. But it's not a bottleneck, as appends continue to scale as we add additional replicas. In general, the commit message adds about an extra 30 to 40% overhead on appends. But the benefit to doing all this extra work really pays off when we decide to read from a materialized stream. So stream replicas actually contain all the updates for any given stream. So that means, unlike before, we can read the entire content of a stream by contacting a single node now, even though even though on the global log they might be interspersed across multiple replicas, where we would have been forced to read the stream one entry at a time. So by placing all the updates for a single stream on a single replica, we gain not only the ability to read any stream entry in that stream, but we can read the entire stream in a single round trip. And as you can see, this greatly increases the performance of a read, especially when there are a lot of entries on the stream that a client needs to consume. So in vCorfu, clients can choose to either have local views or remote views on objects. Local views are basically traditional state machine replicated objects, much like in Tango. Clients follow updates on the stream and play these updates back against in-memory state. Now, materialized streams enable a new kind of view. The remote view enables clients to delegate playback to what we call stream replicas, or delegate playback to stream replicas. In practice, we implement this using Java's remote class loading features. And this enables clients to get the state of an object without playing back the object locally. So remote views are actually really useful when there are a lot of clients playing back the same object that's being heavily updated. So in this graph, we show the latency of reading an object that's being constantly modified. As the number of clients increase, the local views really stress the read throughput of the log, as they're all trying to consume the entries that the client that's modifying the object are producing. So with a remote view, the clients obtain the local version of the object, and only the stream replica needs to play back the object. Local views are still especially powerful because they provide this really in-memory state that a client can query. So in the case of a client that does many reads on an object, the in-memory view may actually be better if the object is not being constantly modified. So vCorfu also supports transactional execution with very strong semantics, thanks to the presence of a global log. So transaction execution is executed optimistically in vCorfu. And the runtime provides really advanced features like read your own writes and opacity. So during optimistic execution, the client tracks the version of each object it accesses. Well, we call this the read set. And it generates a list of modifications that a transaction will make without writing them to a log, and that's known as the write set. So in vCorfu, the object versions are really just a global log address of the last update to that object. To commit a transaction, we leverage a feature of vCorfu we call lightweight transaction resolution. And this feature really exploits the sequencer to resolve transactions, allowing transactions to be decided without being bottlenecked on I/O. Now, this feature is enabled by having the sequencer simply conditionally issue addresses. So when a transaction commits, the runtime sends the sequencer the version of all the objects it has read. So in this case, this triangle object at version 1, and the stream IDs of all the objects it will write to. So in this case, the diamond object. Note that it's not going to send the content of the transaction or the read sets or write sets at all, just the version numbers and the IDs of the streams that it's going to modify. And now the sequencer does a really simple comparison when it issues a new address. If the address of the objects in the read set haven't changed, then the sequencer will issue a new token. If they have, the sequencer will reject the transaction, and the transaction will have to retry. So if the address is issued, so meaning that the sequencer allows the transaction to proceed, the client just needs to write to the write set. Since the address that was issued is guaranteed to have the requested read set by the sequencer. So unlike other systems, a client encountering this entry doesn't need to do anything to determine the read set. So in this case, the read set was a completely different object, right? That in most systems you would have to go, the client would have to go and read. In addition, transaction resolution with this lightweight resolution mechanism has basically been simplified to a simple comparison of two integers. So next we're going to take a look at how vCorfu deals with large state machines, and these are things like huge maps and tables. So large state machines are really problematic because they pose a burden on the log with a large number of updates. And they pose a burden on the client as well, since the client has to play all these updates back in memory, and they have to have enough memory to store the entire state machine that we're replicating. So for example, if this client was holding a 100 gigabyte database, or if the state machine was a 100 gigabyte database, each client would have to have 100 gigabytes of RAM, and this isn't going to be a scalable solution. So to tackle this problem, vCorfu supports what we call composable state machine replication, which enables state machines to be composed of multiple smaller state machines. Now this is enabled by vCorfu being able to refer through any vCorfu object by a simple pointer. And this pointer can refer to not only the latest version of the object, but any version of the object as well. And composable state machine replication reduces the burden of playback by dividing the object into kind of natural components that programmers are able to reason about today in memory. So for example, CSMR linked list would be composed of something like nodes, or a composable SMR map would be composed of things like buckets, just like their in-memory analogs would. So CSMR really leverages the transactional features of vCorfu. And whenever multiple components of the larger state machine that has now been divided need to be touched, we're going to use transactions. So to see all this in action, let's take a look at a map. So instead of having a single large map, a composable SMR map is going to be composed of multiple smaller state machines called buckets. Now this is easily achieved by dividing the hash space up into bucketed regions, just like you would do for an in-memory hash map. The result of dividing this map up into is that most operations will only have to access a single bucket, and these buckets are much smaller than the whole map. So, for example, if you had to access a key named Apple, you would just go to the A to G bucket and pick up your key and access that state machine. So each bucket still has those same strong consistency semantics as any other state machine replicated object. So certain operations like clear or size are going to be more expensive because they're going to end up touching all buckets, but they'll leverage the transactional functionality of Corfu. So for example, checking the size of the big map is going to involve checking the size of all the smaller maps. And we want to make sure that we do this atomically, so we execute a transaction. However, these operations tend to be rare, right? It's not often that you check the size of a map. So we see this as a good trade-off, and if we can execute transactions quickly, it ends up going very well. So to put this all together, the vCorfu YCSB benchmark really exercises all the features that I just described. So to run the YCSB benchmark, we implemented the CSMR map that I just described, and we used remote views to really maximize performance across multiple clients. So this benchmark here was performed across a configuration of 12 replicas in vCorfu. So that would be 6 stream replicas and 6 log replicas, and 12 replicas in Cassandra. And that's this is against 4 client machines with the maximum threading settings. So vCorfu really excels in the read-dominated workloads, since reads only need to access a single replica in order not to return stale updates, while providing strongly consistent cross-partition reads that Cassandra doesn't provide. So in conclusion, vCorfu really addresses the read burden with the 3 techniques that I just discussed: stream materialization, composable state machine replication, and lightweight transaction resolution. And as I said earlier, vCorfu is a huge project that couldn't have been done without the many contributors to both the Corfu and Tango projects that we build on, and the current code base today, which really is a collaboration between academics and also both research and engineering teams within VMware. Finally, vCorfu is partially available as a fully open source on GitHub. Now, the unfortunate part about publications is they're really a snapshot in time, and vCorfu is Corfu is a evolving project. So the source code has very much evolved through time, and that's just a consequence of having an evolving project. So that's the end, and I'll open to any other questions.
So I have a few questions for you. So one, it looks like there's this tension in determining what a stream should be. So if you have more streams, then you're going to have fewer aborts for the transactions. But that requires more state on the sequencer. So have you thought about that? And do you have any sort of guides in telling developers like what a stream should be or what an object should be?
Yeah, so that's an interesting question, and this speaks to how the Corfu system has evolved past what it is currently described in the paper. But it turns out that you might need finer grained support than just resolving conflicts just by if a stream has been modified or not. So we realized over time that you actually need some kind of way for a developer to say what changes really matter, what changes really conflict. That's, I think, the best way to do it is. That lets developers not have to reason about how big streams should be. Yeah.
Okay, great, thank you.
Hi, this is Alex Horn from Fujitsu Labs. Given the complexity of vCorfu, have you run a linearizability checker on your code base? And if yes, what were your findings? And if you have run one, can you exploit the fact that you can decompose state machines into these into the composite parts in order to make linearizability checking more efficient?
That's a pretty interesting question. I'll have to confess that we actually have not run a linearizability checker. I don't know what it would take to do that, so it sounds like a reasonable thing that we should explore.
Yeah. Okay, I have one more question for you. So have you thought about automating the choice between local views and remote views, so developers don't have to do that, and your system figures out what the best thing is for a given workload?
So at one point in time, we were doing runtime inspection of code, and it turns out that that's a huge mess in Java. But it's still really, well, at least that's what we have looked into so far, looking at how long or how often objects are being accessed and determining whether we should access remotely or locally.
Okay, cool. All right, so let's thank Michael once again.